Okay, good afternoon, everyone. My name is Mike Wiggins. I'm with Jeffrey Rader, and I am a application specialist in the feeder division. And I want to thank everybody for attending today and spending a few minutes to learn a little bit more about the Jeffrey Rader feeder product line. That being said, we'll get started with the presentation. Start off with give you a little bit of history about Jeffrey and Rader. We both merged, and by the merger, we have now been able and capable of supplying customers with a lot broader line of products, both on the engineering side from the Jeffrey Rader engineering spectrum all the way through the feeders. We can do complete bid packages now for complete systems with the merging of Jeffrey and Rader companies as one. Anything from wood to aggregate, whatever the industry might be. So we now, with the merger of the two, have a lot more products and equipment to offer customers. And with the merger, we have a lot to do with utilities and power, paper, chemicals, petroleum, and aggregate, and coal, of course. Between the two companies, we have 100 years of experience in crushing and processing equipment, and again, with our knowledge from the engineering side of the Rader, we can do much in the as far as the engineering side with complete system packages. Starting in the vibratory feeder sales and applications, predominantly with feeders. We are predominantly in the aggregate, which is the rock and gravel, and mining, of course, of coal and ores and precious metals. Our feeders are kind of divided into three main groups, first being electromagnetic, the mechanical, and the brute force or twin motors. And these are all unique in their own way, which we'll get into a little bit further in the presentation. Basically, a feeder is used to meter or regulate the flow of material from point A to point B, standardly used under some type of surge hopper or surge pile, and used to convey bulk materials. You can see in the slide here, this is an electromagnetic feeder feeding a belt in line with a belt, and this particular model here is one with a belt centering device, where if you've got an application where you have a belt that's going to be narrower than the pan that's feeding it, you may need to include a belt centering device, which this one has here, so that you won't have spillage over the sides of the conveyor. You can either do this with a belt centering device or with the use of side skirting around there, but in the event that you wanted to use a belt centering device, it can direct the flow of material right to the center of the belt. So that's just an option we can have added to any of the pans. This next slide here is our electromagnetic vibrating feeders. These are available in electronic versions that we can send out in emails anytime you need one. And there's a picture of a typical electromagnetic feeder there. With any electromagnetic or NF feeders, we can supply you a general arrangement drawing, which will show you all the dimensions, the basic vertical height, the length of the pan, the width of the pan, the suspension points, the bill of materials for that. If you need a drawing for any application you're working on, you need an AutoCAD that you can use for lay-in purposes, that can be supplied. It may be one that we previously supplied, but it's for lay-in purposes. It will give you the length and width and vertical height for lay-in purposes if you need it just for design. How do they work? A vibrating feeder is simply a two-mass unit consisting of a driven body and a vibrating deck, where you can see in the electromagnetic power unit here that you have a center clamp, vibrator springs, and a coil. And the spring system is tuned to a natural frequency above the operating frequency. Basically, you have a main frame, which is mass 1, which is going to be driving the pan, mass 2, which is the deck, leaf springs, vibrator bars, and the stator, or the magnet. That's just a side view of a typical electromagnetic power unit and pan. This is a picture of a center clamp with a armature for the electromagnetic feeders. And your vibrator bars on these would be placed in this gap here on the center clamp. The housing for the electromagnetic design, these are for EF series. They're cast for our EF 3, 4, 5, and 6 models. The EF 8 are going to be a welded mainframe instead of a cast. This is showing a picture here of your coil and the electromagnetic. Here we got it broken down where you got your magnetic assembly. You've got the coil, the armature, your center clamp, and your air gap. That's all the internal components that make up the electromagnetic power unit. The basics of the Jeffrey Rader brand electromagnetic feeder is controlled by high-frequency vibration, and this is accomplished through the use of electrical pulses in conjunction with a mechanically tuned machine with mechanical resonance frequency slightly different from the electrical frequency of the power supply. And basically what's happening here, you have a coil which is energized and uses your magnetic force. And then when it's energized, the armature pulls the coil back. Vibrator bars are deflected, and you have an SCR in your control, and this SCR blocks the current to the coil, therefore releases the bars and causes deflection, which acts as a spring to cause the vibrations. And the electromagnetics, this happens 36 cycles per minute for 60 hertz and 3,000 cycles per minute at 50 hertz, and these are tuned to a stroke of 70 mils. It's basically showing you here the line of drive for electromagnetic feeder, where you have your power unit and you have your line of drive going through the pan. Electromagnetic units, the speed is constant, so you're basically controlling the voltage to the coil, and then you have 100%, 0 to 100% variable range in your control of the electromagnetic feeders. As I said, 3,600 cycles per minute equals 70 mil stroke at 60 hertz, and at 3,000 cycles per minute at 50 hertz. A manual auto circuit and sets 4 to 20 milliamp feedback signal from your PLC. So if you wanted to control it through your PLC, you do have that option with the 420 milliamp signal. All the controls for the electromagnetic feeders are CSA approved. Our standard control cabinets, NEMA 12 enclosure. Standard offering, we can offer a NEMA 4, NEMA 4X. We can also offer for specialty applications a control that could be considered a high-low. If you need to regulate material and so forth, we can provide a high-low control. All you need to do is let us know, and we can figure those when we're sizing the feeder for you. This is a picture in this next slide here, basically of the inside of the cabinet for one of our MLV controls. One of the offers that we have, if you have an older style HP series electromagnetic feeder, we do offer a replaceable EF series with a replaceable coil. Some of the older generation HP models have an encapsulated coil, which requires you to replace the whole stator. If you go to one of the newer version power units with the replaceable coils, we'll give you a new 2-year warranty on that unit from the time of purchase. So it gives you the option in the long run of having a replaceable coil versus the encapsulated coil. So it's less maintenance, and also it's cheaper in the long run as far as replaceable parts. So that's an offer that if you have one of the older HP series consult us and we can give you a newer version, HP or EF style replaceable coil power unit. As far as tuning on the electromagnetics, we have the air gap set at 93 thousandths versus some of our competitions of 85 thousandths. By doing that, we have a larger amp draw, but we can provide more capacity per deck size with less of a amp draw. Deck amplitude is tuned at 70 versus 62. So of course we have a larger gap there and larger stroke. As far as electromagnetic units and standard 460 volt, we stock an EF3 36 by 60 and an EF4 42 by 60. These are both complete units ready to ship out of inventory based on aggregate applications at 100 pounds a cubic foot. These units will do approximately either 600 for the EF3 or 700 for the EF4. So say these units are standard stock units that can be shipped within a day or so, providing that the customer has the correct voltage that they need. If we have to convert it from 460 to 575, we'd probably have about a week turnaround time for those. But just keep in mind that the EF3 and EF4 are stock units. Stock power units, 460 volts, we stock EF3, EF4, EF5, and EF6. Of course, the EF5 and 6 require larger control cabinets, but we have these power units that if you have an existing unit and one of the power units go out and you need a quick turnaround, we can ship these out right away. As mentioned earlier, the air gap is an important issue with the performance of the feeder. Having the correct air gap will cause the unit to work at its optimal performance, whereas if you get an air gap that's is not at the correct setting, it's going to cause the unit to either hammer or can cause a loss of capacity. And basically, the following procedures is recommended for making these adjustments: removing the top cover and taking care not to damage any of the dust seals on the cover itself. You use feeler gauges to check the air gap and make adjustments necessary. On electromagnetic feeders, the air gap should be set at 93 thousandths. And with the use of feeler gauges, this can be adjusted accordingly to make sure that the unit is working at its most proper value. Here's a picture here of the inside with the cover off of an electromagnetic EF style series, and what you can see, this is where we have the replaceable coil in here versus the encapsulated coils, where if you have one of the older style generation feeders that has an encapsulated coil, we can upgrade it to one of the newer versions like this one, where the coil itself is all you have to replace when the coil goes out, instead of replacing the whole armature. So this is a big benefit, for keeping downtime at a minimum if you can go convert these over to those style units. Every unit will be supplied with a metal tag showing you the model, the serial number, the year of manufacturing, voltage, hertz, and phase, and so forth. And these are important because if you have to do a replacement somewhere down the road, if you can just supply us with that serial number, we can go back and tell you everything about that unit as it was when it was shipped. So that's really important to make sure that your tag stays intact with that unit or kept a copy of somewhere so that we can track everything back to that serial number. Now, as far as replacements, these are some of the recommended replacements that we would suggest that you keep in stock. Fuses are very important. Control firing board. SCR. Vibrator bars. And liners. Out of all of these, probably the most important that it would be most useful to have in stock on the shelf would be the fuses and the control firing board and the SCR and the coils, because if one of these go out, most likely the unit's going to go down. So that would those 4 items there would be highly recommended on keeping as a stock item. Here's a couple of pictures here of some of the unique deck designs that we provide. Based on the application, if you need something where dust is going to be an issue, we can provide, this is a tube design here, which can be totally dust tight. And also, here's another tube design here with an overhead power unit. So if you've got a vertical height issue, then this may be something you would consider to use to get away from that. If your belt's really close to where you're feeding, you may want to consider using an overhead power unit for vertical height issues. So these are just a couple of different designs here that we offer, whether it be an overhead power unit, below deck power unit, or enclosed tube type. Types of exciting force used to operate, frequency of operation, amplitude of deck stroke, type of spring utilized. Cost effectiveness on electromagnetic, you would consider using on the smaller units electromechanical, on the larger units. On the smaller units, you want to consider our HP or an EF. When you get up to about a 42 pan size, you would probably want to look at going more towards electromechanical from a cost standpoint. I mean, those are some of the advantages of using electromagnetic over electromechanical. Some people are more comfortable with mechanical side versus the electrical. It could just be a matter of preference. Customer preferences due to existing equipment, spare parts, and things they keep for other units, the control, and explosion-proof environment. So if you've got to have an application where you need an explosion-proof rated unit, then that's going to eliminate the electromagnetics, because those are not rated for explosion-proof applications, whereas the electromechanical, that can be done through the use of an explosion-proof motor. So that's some kind of the differences that you might want to consider when looking at electromagnetic or mechanical. Whether it's explosion-proof rated atmosphere, the control, you might have a little better control with electromagnetic. And then when you get into the larger deck sizes with much larger material, you want to look at a electromechanical. A couple of pictures here of electromechanicals in use out in the field. The one to the right over here, if you look at the end of that deck, you can see a grizzly section that's been incorporated into the design, where if you've got an application where you need to screen off certain size material, that can be done through a grizzly bar section. So that's another option there of the uniqueness for scalping material off in an application if you need to get your undersized or oversized material out. Here again is another picture of our electromechanical vibrating feeder brochure, which is also available in electronic version if needed. We can send out at any time in an email or whatever fashion you need. On the electromechanical, the drive consists of an electric motor, a positive drive belt, and eccentric shaft. So a little bit differences between the mechanical and the magnetics. In the mechanicals, you have a motor, and in the magnetics, you have a coil and an armature. The motor rotates the eccentric shaft, causing reciprocating force. This force reciprocates due to the natural frequency of the spring system. This causes the deck to vibrate. In these, you have coupling springs between the exciter box and the deck, wherein the electromagnetics, you have leaf springs in the exciter box, which acts as your coupling springs do in the mechanicals. So same concept, which is a little different design between magnetics and mechanical as far as the type of vibration or how it's vibrated. Again, there's another drawing that we can supply, whether it be mechanical or magnetic. for if you need something for lay-in purposes or just for dimensional purposes, we can supply you something that we've previously done in the past. We don't suggest you use these for construction purposes, but just for lay-in purposes, if you need something just to see if it's going to fit in, that we can usually find a drawing on something that we've already built that can be used just for lay-in purposes. With the mechanicals, of course, you have an exciter box, you have the deck, the compressed coil springs, which do not have a pigtail, they're flush ground, stabilizer bars between the box and the deck, motor, drive belt, and exciter shaft. You have a shaft with eccentric weights, motor, cog, drive belt, positive, no slippage, flange bearings on each end of the shaft, which can be replaced, and these are tuned at 5/16 strokes at 900 cycles per minute. The advantage of electromechanical magnetics also is that it allows you to have a bigger stroke, whereas if you've got larger materials and you need that bigger throw to move the material over the pan, you get that more so with the 5/16 stroke versus the 70 mils on the electromagnetic. So you have a bigger stroke, which is good for when you get an application with the bigger pans and bigger materials. So you kind of want to, once you get above a 36-inch wide pan, in most cases you're going to look more towards a electromechanical versus electromagnetic just because of the pan size and the stroke. Here's the inside shot here of the exciter box on electromechanical. Of course, you can see the motor, you can see the positive drive belt, and your eccentric shaft back here with the weights on it, and your flange bearings. And basically, you have this eccentric shaft with weights on here, and that's how you adjust the stroke, by adding or taking away weights off that eccentric shaft. This is a picture here with your coupling springs between your exciter box and your deck here. So basically, when that shaft turns with the eccentric weights on it, it causes the vibration, which is transferred into these springs and then transferred to the deck itself. Here's a picture of the eccentric shaft with the weights and the flange bearings on each end that mounts into the box. There's a picture here of the exciter box prior to being mounted to the pan. As you can see, here on the end, the coupling springs that would transfer the vibration from the box to the pan. Another picture here of our controls for the electromechanical feeders. A little bit different design than the MLV controls for the magnetics. Still can receive a 420 milliamp signal to interface to customer's PLC. As far as the workings of the mechanical voltage is constant, and you change the speed by alternating the hertz to the motor, which is done through your VFD. So in the mechanicals, you can control the stroke basically by controlling the hertz to the motor. You have a 0 to 100% variable range on the control, manual auto circuit. Again, it sets the 420 milliamp signal from your PLC. We use a Toshiba NEMA 12 VFD. Other brands can be supplied at customer request. We just need to let us know what the specs are and what particular brand you're looking for, but we can supply other than the Toshiba. All our controls are UL approved. They include dynamic braking resistors to burn off regenerative energy. Again, with electromechanicals, we also supply a metal name tag with the typical information of the type, the size, the stroke, the horsepower, the RPMs, and the serial number. And these are very critical in the field when you got to have replacement parts. And if you just give us that serial number again, we can tell you exactly everything about that unit when it was shipped out. Some of the spare parts recommended for the mechanical feeders is your stabilizer bars, which are mounted between your exciter box and your pan. the coupling springs, of course your bearings, your positive drive belts, and your liners. One thing I'd like to mention real quickly about liners. Liners are very critical to the performance of the pan, keeping the pan from wearing. Also, it's very critical that whatever the machine was shipped out as far as liner thicknesses is maintained throughout the life of the machine, because these are tuned machines, and it's tuned to the deck weight to the box. In other words, if that unit went out of here with 1/4-inch liners in it, and they lasted a year or so, and then you say, well, I'm going to go back and put thicker liners in there. I'm going to go from 1/4 to 3/8 or 1/2. That's going to cause an issue with the tuning of the unit, and it's going to probably most likely cause you to lose stroke and therefore lose capacity. So anytime you want to look at replacing liner thicknesses other than what the machine was supplied with, you need to consult engineering and let us look at it to make sure that the tuning will not need to be changed as far as the weights on your exciter shaft because of that additional weight added to the pan. So it's real critical that you maintain that deck weight relationship with that box and not change anything or add anything to it. So anytime you want to change liners and look at going to a thicker style liner, then you really need to consult us and let us look at it and make sure that's going to be okay and not cause issues with the performance of the feeder itself. You can see in this picture, as far as liners go, we offer a variety of different combinations from AR-235, AR-400, 304 stainless steel, UHMW tie bar, specialties such as ceramic, rubber, chromium carbide overlay, and etc. Again, the main thing is that you keep the liner thicknesses constant, and if you do have to make a change or want to make a change, if you let us know so that we can look over the tuning of the feeder as it was shipped out. For all models, whether it be mechanical or magnetic, we offer as an option cable clamps and thimbles that you can use to suspend it with. On NF, there's another option. We offer a 10-foot pigtail, which allows hookup without having to open the back of the box and wire into the wire junction box on the motor. We would supply that 10-foot pigtail, which would come out of the side of the box and can go straight to a junction box from that point without having to open the box up itself. And we also offer a variable frequency drive to the Shiba for the NF style feeders. That is also an option. Again, with the electromechanicals, we have a variety of different deck configurations and styles that we can offer. As you see in the top picture here, again, this is a tube type where if you got an application with a lot of dust and you need to keep it contained, these can be totally enclosed between the infeed and the discharge ends of the pan. Here you can see a bias cut pan in an application where you might need to evenly spread material onto something. You can do this through the use of a bias cut pan. And this one below, again, this is a rectangular covered pan where you have a round inlet, and you can have a vertical discharge off the end of the pan, or you can have vertical or horizontal discharge. It doesn't matter, whichever customer preference you have on there. But again, these are just some of the different combinations of pan designs that we can offer. Belt centering devices, grizzly sections, as mentioned earlier. Heater blankets is another option that we can provide, where if you're in an environment where your pan may freeze over with material on it due to really cold, extreme temperatures, we can supply heater blankets which can eliminate the material freezing and sticking to the pan and the bias cut. Any kind of pan configuration you might have, give us a call. We can always look at doing any type of configuration, hopefully to meet the needs of your application. One of our latest designs in the electromechanical is what we are calling a Centroload feeder. and this is a design we came up with to feed cone crushers. And this one is unique that it has a bottom discharge, cone discharge here, which helps in regulating the flow of the material right to the center of the cone. One of the important issues with this design is that it's limited in width and length and also material size. That when you get above any material size than 8 inches in diameter, we don't recommend using a cone style design. So any of the applications where you want to consider this, you need to have material at least 8 inches or smaller in diameter. You can see a picture here where we're feeding a cone here, and of course you can distribute the material right in the center of the cone, choke feed it, and I had a lot of customers claiming they get a lot liner life out of their cone crushers by feeding it this way. The equal distribution of non-uniform product improves cone crusher efficiency and improves cone crusher liner wear life. As far as application goes, for larger capacities, widths up to 7 feet and lengths up to 15 feet, wet sticky materials and impact loading, we would consider what we would call our brute force feeders. Anytime you're looking at an application, we would consider capacity, the types of the material, size of the material, the density of the material, the angle of the repose, the moisture content, the characteristics, whether it's wet, sticky, abrasive, and determining all these are important factors in determining the width of the feeder and the length of the feeder, because all these in combination will determine what size feeder pan width and length is going to be required for the application. In addition to normal applications, we'll assist you in proper hopper design, and we can't stress enough that to get optimal performance out of your feeder, following the recommended hopper design is very critical to get your capacity needed out of the feeder. As you can see here, a sub-hopper above the feeder where you have a 60-degree angle on the back slope and 50 to 55-degree angle on the front slope. And these are recommended angles that we like to see to keep the load of the material more on the slopes of the sub-hopper versus the pan. It's really very important that you follow the recommendations that we provide with every feeder, that you follow these recommended hopper designs to get the best performance out of the feeder and not damage the feeder. As mentioned, recommended hopper configuration for efficiency, material flow from the hopper. Some general rules should be followed. The rear wall should be a slope of 60 degrees and the front wall 50 to 55. But again, that's to help eliminate head load on the pan itself and overburdening the pan. And as far as the gate height should be twice the largest piece size of that material with the normal size distribution. You need your gate height at least 2 times or more. If not, if you had material size 8 inches and you only had your gate set at 6, if you had 2 pieces of 8-inch material coming through that throat or gate at one time, they could wedge and bind in the hopper there and have to be cleared out. So as far as the hopper throat dimension, it should be approximately half the gate height. If the throat dimension is increased dramatically, then what happens, it ends up causing a burden or head load on the pan, which is going to restrict vibration and cause the feeder to lose capacity and even could cause damage to the feeder itself. This next slide here is basically showing the hopper width dimensions and so forth, and the clearances that we recommend between the side walls of your pan and the side walls of the side skirts coming into the pan. You want to make sure that any of the side skirting coming into the pan on the sides has at least a 1/2 inch to 3/4 clearance, so you don't have any interference between your side skirting and the bottom of the side skirting coming in contact with the top of the liners on the bottom of the pan. You don't want anything that's going to rub the pan or cause interference, because any interference or touching of the pan is going to cause the feeder to lose vibration by restricting the vibrations of the pan through the side skirts, whether it be through the rubbing on the sides or the bottom of the side skirts. Installation of the skirting, and to say, to obtain the required capacity of some feeders, it is necessary to convey material at a depth greater than the sidewalls of the pan. Typically, most of our feeder sidewalls are going to be 6 inches in height. So in a lot of cases, you're going to have material on the pan depth anywhere from, it can be anywhere from 4 to 20 inches in depth. So you've got to maintain that material height through the side skirts, and you just want to make sure that you have proper clearance between the side skirting and the sides of the pan itself. And also that the side skirts run the entire length of the pan to retain the material in there. And as far as the feeder length, we like to have the pan at least 6 inches of free space at the end once the feeder is shut off and it reaches its natural angle of repose. You don't want the feeder to free flow onto your belt or whatever your crusher that you're feeding into. So you always want to make sure that once the feeder is shut off, that the natural angle of repose material still has, once it reaches that, still has at least 6 inches left on the end of the pan to eliminate any free blowing off the end. As you can see here, if you have too large of a throat, it causes a burden on the pan, and it can cause damage, restriction, or movement, and as I say, even damage the feeder itself, damage the vibrator bars. The vertical front or rear walls, when the hopper front and rear walls are tapered to help support the material load, the hopper, when either wall is vertical, all the hopper load is reportedly directly to the deck. So you want to make sure that you have proper angles on both the rear walls and the front walls of the hopper to eliminate any direct column loading onto the pan itself, and keeping your gate height where it should be set so that you can make sure you don't have any bridging in the throat or the gate of the hopper. With every proposal that we send out, we will provide a recommended hopper design, basically based on your application information supplied, based on the pan width and length and the desired capacity, and the density of the material and the size of the material and the angle of repose. We'll supply you a recommended hopper design showing you the gate height that material is needs to be, the throat, the angle of the repose, the angle of the downslope of the pan, and the E at the end of the pan, which is the dimension that's after the material reaches the natural angle of repose, how many inches of free space is left on the end of that pan. So we will provide with every proposal a recommended hopper design. We'll give you these, which are critical in providing the optimal performance of the feeder itself. I want to thank everybody for attending and hope they picked up a little bit of insights here today. And if anybody has any questions or anything. Okay, again, if nobody has any questions, I want to thank everybody for attending today, and hopefully the next time you need a feeder, you'll give us a call, and we'll be glad to help you in any way we can.